So there are a couple of ways the predictor of the previous example can be improved. One of them is to add a little bit of global history to the prediction. So what we have here is a possible execution path of an application, and let's say that we have one common execution path that follows the red line over here, and the branch predictor will quickly learn that we take the left path of the first branch and that we take the left branch of the second path. That's good. But we also have another fairly common path of execution through this code, and that's the blue path. So on the blue path, we take the right, and then we take a left, and then we take a right. So if we have two common paths like that, let's say that they are equally common, and let's say that we every other time take the red path and every other time the blue path, the branch predictor is going to get very confused. So what we would like to do is to add a little bit of global history to our prediction. So when we're going to make the prediction down for this branch over here, instead of just looking at the address, the program counter of this branch, we're also going to ask the question, which path did the execution come from? Did it come along the red path, or did it come along the blue path? We add that information to our guesses, and the accuracy is most likely going to be improved a bit over the previous prediction. What we are going to do is simply to add a little bit of global information. We're going to, in this example here, I add information about which direction the last three conditional branches have taken, left or right, and just symbolize each of those with a bit, and just keep updating this, which way did the last three branches take. We're going to also, so we're going to use those 3 bits in combination with some of the bits from the program counter when we choose which of these entries of this vector we're going to turn to when we make our prediction. So both the PC but also the history where we came from. So this is what's called adding a little bit of global history, and the pro of this is of course, from my previous example, it looks like we can make a much better prediction. But there is also a drawback of this, and that is that each program counter now, each address, each instruction now will create 8 different entries into this vector. And so this will require more entries of this vector, 8 more entries to remember how keep history for the same number of program counters. So it's a hardware cost. This is typically called an NM predictor with N levels of global information and M bits in the prediction. So in this example, this would be a 3,2 predictor. We have 3 global bits and we have 2 of the prediction bits. Turning now to the second of the examples we looked at before, and using this, adding this global predictor bits as well when we index into the predictor vector here. What is the outcome? What is the outcome of using the global? Will this make the prediction more correct? Will it be the same? Or will it be less correct? You can also try to come up with the number of mispredictions you think would happen when you execute this code. So the correct answer is that it will indeed get more correct. And the number of mispredictions you will have here is roughly going to be 2n instead of 4n as before. And the intuition to why that is that when you come to the point in time when you change the value, okay, so you make a prediction, you're going to make the wrong prediction here. You come from predicting zeros. The first time you were supposed to write the 1, you're going to make the wrong prediction. But once you made that wrong prediction once, that means that you're going to see the last branch is going to say 0, 0, 1, where 1 was the last outcome of a branch globally in the system. So that 1 there will always when we change from 0 to 1, that's going to be a 1 in the most recent entry here, which means that we're going to hash for all those entries. We're going to hash to a special location, and that location is quickly going to learn that we indeed are more likely to take those branches. So we are only going to make one mispredict here every time we change from a 0 to 1, and then of course when we change from 1 to 0, same thing, we're going to make one mispredict, but not the two mispredicts that we did before. There are actually quite a lot of different proposals how to do the branch predictor, but the most common one is the two-level predictor with some number of global bits and some number of hysteresis bits. And as I said, a 3,2 predictor is quite reasonable. But there are other predictors as well, and there is, sometimes some predictors suits one application better than some other predictors. So it's fairly common that you implement what's called a tournament prediction, where you actually implement a couple of these prediction algorithms, and all of them are going to sit there and make their guesses. So you have, let's say you have 4 different green men, and all going to sit there and make their guesses over and over again. All of them going to update their own local state so they can make their new predictions. And you're going to have you're going to see which of these green men seems to be the most accurate man right now. So you can dynamically starting to listen more to the green man that's been right the most time. Let's say the last 100 predictions, who's been the smartest of the 4 men, and then you listen to that little green man, and then you turn to some other green man when it starts to be better. So so this kind of tournament prediction can up your accuracy a little bit, and I just entered some performance numbers here, just comparing if you only have a 2-bit prediction compared with if you have a 2,2 prediction. No, it's not always that the 2,2 is better. Sometimes we can outsmart ourselves with those kind of algorithms. So if you have a tournament prediction where you sometimes listen to the just 2-bit prediction, and sometimes you do the 2,2 two-level prediction, then you can actually decrease the overall misprediction. So now when you can make correct prediction, the other part of the equation is where the heck are we going? So the outcome of the branch, the last pipeline stage, that's when we know the outcome of the branch, but that's also when we know the address of the branch to. And if you're going to make this prediction already in the instruction fetch stage, well, we somehow also have to predict where we're going to jump to. And we do that by this branch target buffer that is organized like a cache. So you take the PC, some index bits of the PC, you take the most significant part of the PC, you compare that to some kind of tag, address tag that's stored in this prediction cache. And if there is a match, then you know that the fields of the data that's associated with that tag actually stores exactly the information about the branch that you're executing right now. So you can store lots of different kind of information. For example, you can predict the target of if the branch is taken. You can store some of the whether it's taken or not, that kind of information into this branch target buffer as well. So the branch target buffer stores information about the taken instruction, and this, of course, as I already said, branch target buffer is integrated in the fetch pipeline stage, instruction fetch pipeline stage, because that's the point in time in the pipeline where you need to make these guesses. And also, as we discussed before, we also have to make really sure that the speculative execution that started based on one of these guesses cannot have any side effects on the state of the processor. You can make this branch target buffers actually quite intelligent and quite efficient. So it's not uncommon that the branch target buffer not only stores the address of the next instruction, could also actually contain the next instruction or the next few instructions as well. So instead of having to fetch the instructions from memory if you're going on a new execution path, which potentially could involve cache misses and so on, you can store the next few instructions themselves also in the branch target buffer. So while you don't have to wait for the instruction fetch to actually take effect along this new path, just execute whatever instructions are stored in the branch target buffer. Another trick that you can play is what's called folding branches. So far, we talked about conditional branches and figure out the outcome of them and also figure out where they're going. But you can also store unconditional branches in the branch target buffer. So it's an unconditional branch, and here, of course, you store the target address of the unconditional branch. So you know which instructions to execute next, and if the instruction fetch implementation is really smart, and instruction fetch sees that it's about to execute an unconditional branch, and let's say that the branch target buffer contains the instruction of the target, that means that the instruction fetch stage, instead of executing an unconditional branch, when we know exactly what's going to happen, we're going to take the branch because it's unconditional. We know the target. It's always the same target. So instead of executing that branch that we already know the outcome of, we actually could swap it and instead execute the target instruction. So that means that that the unconditional branch can actually execute in 0 cycles. We don't have to allocate any kind of pipeline resources beyond the instruction fetch stage. So this is called branch folding. Unconditional branches executed in 0 cycles. The last thing we're going to talk about is how to handle calls to functions or procedures. So what I have here is just a picture of maybe some execution path of some kind of program where the branch will jump to some new basic block and start executing there. And in this code, we have 2 calls to the same function or procedure. So we call A, and of course, as we know that we're going to make a call to that procedure, we're going to execute this instruction, we're going to return from the call, and we're going to continue executing. Same thing when we call that procedure the second time. Now the question is, how good of a job will this branch prediction and the branch target buffer be able to do on these calls and these returns? Well, actually, potentially, the branch target buffer can do a pretty good job, and the branch prediction on the calls to the procedure, because they can figure out that if we execute because this will look like a branch instruction to the pipeline, right? So we will have the same question to where it's going to be taken. Well, that's an easy one. It's a procedure call, so it's going to be taken. But where are we going? That branch target buffer information, that really depends on the instruction we're executing. So we will actually do a perfect job here for these calls. However, when we do the returns, the branch target buffer of the very last instruction here cannot know where we're going to return to, because sometimes we make a return to this address and sometimes we make a return to some other address. So clearly we need a different kind of support if we like to remove the bubbles in the pipeline when we make the return from this. So we have implement something which is called return address stack. So just stating the problem that we see in the previous example here, that the branch prediction and more correctly actually the branch target buffer may be very confused. So a new approach that we need to be taken here is to implement a new hardware structure which is called the return address stack. That means every time we make a call to a procedure or a function, we're going to push the address that we are calling from on a small stack, and every time we return, we're going to pop the address from that stack, and we're going to use the pop exactly that same address incremented by 4, and then use that information as our next instruction returning from the call. So a return address stack.